All right, so look what I'm going to do. I'm going to draw another picture here. So I'm going to look at the line from the top. So let's say this is x and this is y, Cartesian coordinate system. So this will be z like that. X cross y is z. So I'm going to look from the top. Okay. So looking from the top, or just to stick to my notes, I'm going to look from the bottom. In other words, I'm going to look at the xy plane. I can either look from the top or the bottom, doesn't matter. But because of the way my notes are structured, so I'm going to look such that I see the current going into the board. Okay? If the current is going into the board, then the magnetic field lines will be making circles. Okay? Will be making circles like this. What does that mean? This means that if I am at a fixed distance, let's say d, at a radius of d away from the center, so, okay, away from the center, the magnetic field will be constant anywhere on this circle, and it will be going in this direction? No, the other direction. This direction, right? Okay, so anywhere along this line, the field will be constant. If I take another circle with a different radius, d2, then the field will be constant along the second circle. So I can represent this. What I'm going to do, I need some space. So I'm going to integrate B on the contour, okay? So any of these contours, so I can take this one, let's say C1, okay? Let's say C1. I'm going to integrate along the contour of B dot dl. So this is a contour integration. In contour integration, if we do this, it means that the contour is closed. Okay? You start at a point and you go to the point you started at. All right. So now we know what B is. We found it out, right? So I'm going to put mu naught, the permeability of free space, divided by 2 pi I r, 1 over r. I don't need to integrate over that. Why? Because r is constant. So I can take that out. So that will be d here, right? Integrate of phi dotted with r, the arc length r, d phi r, d phi d r. No. Phi is the direction of the B, correct? I'm going to integrate along the arc. So the arc length is r d phi. The direction of the arc length is phi hat. Okay? By the way, all the notes are updated up to the end of chapter 30. All right? And I made some corrections. Yes. Okay. All right, so this is C, closed contour. This comes out. This comes out, but it is fixed, so the D cancel with the R because I'm integrating over a contour with a fixed R. And so right now, phi hat dotted with phi hat is 1. Integrating of d phi over the contour, so I'll end up with mu naught divided by 2 pi I. The d cancel with the d that comes out multiplied by 2 pi. So I'll end up with mu naught I. All right? Yes?
Why there are 2 phi hats?
Because one, I'm integrating over the contour. Integrating over the contour of what? Of B. I'm integrating B over the contour. B is a vector. The contour is a vector. Yes?
So what are
and one of the other, and one belongs to D phi. And that's what I said orally, okay? So that's when we dot them. When we dot them, we get 1. So we reached a very, very important conclusion. The conclusion is so important, we give it a name. Ampere law. Okay? Well, look carefully. If I were to integrate, do the same thing over a different contour. Guys, look at this very carefully. I'm going to integrate, do the same thing, but not over this C1. I'm going to do it over C2. Will I get the same or not? Does the contour radius information matter? It doesn't matter because do you see the result here is independent. This is not a function of the radius. Do you see that? Very, very powerful result. That's why we call it Ampere law.
But then when you integrated it, you got C, which is equal to T by 2 pi d. That's how you cancel out the d.
But the d cancels with the d, and the 2 pi cancels with the 2 pi.
But then if you have the second contour, the radius would be different.
And this would be different too. Right? The value of b would be different, and the contour over which b will be different, but the d's cancel. Okay? Good. All right? So I'll end up, so the Ampere's law, it says, Ampere law is a generalization that I will prove to you in a second. But Ampere's law says that if you integrate a b, any b, over a contour, which contour? The only condition that the contour has to be closed. The contour has to be closed. Okay? What will you get out of this? You will get a constant mu naught multiplied by the I that is enclosed by that contour. Incredibly powerful result. Okay? The I, which I? So I can do this better with color. I can take the I, take the C, okay? Just to emphasize, you don't have to change that in your notes. This I is the I that is enclosed by the contour. Gents, please, lots of noise from here, please. Okay, because the mic picks up everything. By the way, the lecture videos are uploaded on Learn. I don't know, have anyone had a chance to go and see them? I look like a movie star. No, actually, I don't. No wonder I'm here, not in Hollywood. Yes. Excellent. This is the parallel to Gauss's law. Yep, absolutely. The moment you've been waiting for. This is the parallel to, or the analogous law to Gauss's law. Now, why is it important? Just because it's a law? No, because it's going to help you solve many problems. Remember Gauss's law? It helped us solve many problems. Same thing here. But please, look at this carefully. The physics is different. Don't think that the physics is the same. Many people fall in this trap. They think that this physics is analogous to that physics. No. This physics is mysterious, okay? Yes?
I have a question, like, for that expression of the field yesterday, we found, like, or last time we only found that works if A is much greater than Z. So is that hold, does this Ampere law only hold?
You said this expression is valid? No, this is valid anywhere. This is for an infinite line. That you're talking about a loop. Do you see that? When we had the loop, we had the situation that he mentioned. Right? This is not a loop. This is a line which is infinite. Okay? So, now, just next I want to show you, right here, okay? I want to show you that, okay, that how can be a contour like this give me the same result. So this is what it says, is that what this says is that integrate B, if I integrate B, a along a contour that is closed, I'm going to get the I that is inside of it. So if I have no current inside the contour, you're going to get 0. That's it. As simple as that. So a quick proof is that we take a generic loop. It has to be a loop. Okay? And I divide it into many angles like this. Okay? I divide it into so many angles. The finer, the smaller the angles, the finer the approximation that I will get. Okay? And I will approximate the curve between each two angles as an arch. Okay? So this, I'm going to approximate it as an arch centered here. This one here, arch centered here. This one, an arch. Even though it's concave in different direction, that's fine. Because the finer the angles, the finer the difference between the angles are, the finer the approximation. So this is going to be like this, like this, like this, like this, like this, and so forth. Okay? Engineers, we love to approximate things. If you do this in the limit, if this delta phi shrinks to 0, you have a very, very good approximation. What's the proof? Well, the proof, you can write a very simple code to find the length of a contour. What is the length of the contour? Integrating 1 over that contour will give you the length. That's from calculus. If I integrate constant over a certain contour, I'll get the length of that contour. So here, we have integration between this angle and this angle, plus this angle and this angle, and so forth. So let's write this down. So first of all, just to convince you, I'm going to integrate between phi 1 and phi 2 of this particular curve, this particular arch. So integration from phi equals phi 1 to phi 2, b dot dl. The contour is not closed here, right? I'm just integrating over this one here. Contour is not closed. What will I get? Mu naught I divided by 2 pi. Where did I get B? B is the field due to a current that is going into the board, just like what we have there. Same, I did not change the current. Okay? So I have I divided 1 over R1. So this radius here is R1. So it shows up right here, R1. Okay? So now I integrate from phi equals phi 1 to phi 2, phi hat dotted with R1 d phi phi hat. Okay? Well, I'm integrating over an arch with a constant r. So the r1 comes out, cancels with this. So I'll end up with mu naught I divided by 2 pi, integrating phi dotted with phi again is 1. I'm integrating d phi between what? Phi 1 and phi 2. So I'll quickly put that as phi 2 minus phi 1. Everybody agrees with me? Yes. Excellent. Now you see where I'm heading? I'm going to sum the integrations over all these contours. First observation, does this integration depend on r or the radius of that arch? Nope. All right, so the integration b dot dl closed contour, okay, will be mu naught I divided by 2 pi I. I missed something here. No, I did not. The I is right here. I thought I missed the I. Hold on 1 second, okay? And then I have summation, phi I minus phi j, I, actually I can take this to be I minus 1, I equals 1 to n. See? So the higher the n, the finer the approximation. Each one is independent on the radius. So Ampere's law is proved. Someone had a question, and then I'll go to you. Yes?
How did you know to choose that R1 and not radius closer? The radius changes for that contour.
Absolutely. But for each segment that I'm integrating, the result is independent of R. And there's the proof. Yes?
Yes, why are there two i's on the right-hand side of the equation? Like mu naught I times I.
Here? Oh, because I made a mistake. Thank you. Mu naught, so this is mu naught. Okay? Very, very, very simple, but very powerful. Now, look what happens to this one here. This is the sum of all the angles from 0 to 2 pi. All of them. So you'll get 2 pi here. So this is 2 pi. The 2 pi cancels, and we have a proof of Ampere's law. Ampere law. Not Ampere's, sorry. Ampere law. All right? If I thought of this before Ampere, they would have called it Ramahi's law, but I'm just 200 years late. All right, any questions about this? Fully understood? All right, what about yes?
Sorry, so did you say that that's for current enclosed by the contour?
Absolutely.
So if you were to have like two infinite wires, like one like going like out and one going in, and then you enclose it, so your field would be.
If you have two current lines, one going in, one going out, because we have to do algebraic sum carefully. So one is going in, one is going out, they cancel. It seems like it's magic, but we can prove it mathematically. You see? In other words, if I were to have one here, let's do it outside of this so that you don't get mixed up. So I have a current line that is going in, and I have another current line that is going out. Okay? So this is I and I1, and this is I2. Okay? If I take a contour like this, any contour that surrounds this I will give me any contour, the integration of B. Let's say there's a B somewhere. I don't know what caused that B. Okay? I integrate that B along this contour, I will end up with 2 pi, mu naught multiplied by which I? The blue I. If I do it here, I'll get just enclosing this, I will get mu naught I2. But let's say I take a contour that goes like this. I will end up with 0.
Is that assuming the currents are the same?
This is in, this is out.
Okay, but they have the same.
Sorry, you're right. If I1 equals I2 in magnitude. Okay? All right. Okay. So now we can move on and solve interesting problems with this. Yes?
So you know how to do the unit vector, right? You assume that it's one direction of
Here? I took it to be in the direction of phi. So this is, so I integrated in that direction. So I have to be consistent. I have to integrate over the loop in one direction. Okay? You see, what if, just hold on 1 second, what if I had a plane like this with a current piercing it, okay? But I were to take my contour in a plane which is slanted, not necessarily flat, not necessarily orthogonal to the direction of the current. The same thing applies. Absolutely. We can have a contour in 3 dimensions and divide it into contours that are arches, going down, going up, doesn't matter. Why? Look, guys, because here, what is the integration over this of B? So if I have to connect them, some of you might say, you know, I'm not comfortable with this. I really need, you told us that it has to be a closed contour. So if I were to connect them like this, okay, what will be the integration over these parts? 0. Because B is pointing in orthogonal direction to this direction. So this contour is in the R direction. The B field is in the phi direction. You dot these, what you will get? 0. Okay? All right. So let's look at an important problem. Actually, it's a problem that has practical implications in designing transmission lines. So what is the problem? The problem is this. I have a wire, a thick wire, which has current flowing. Yeah, sorry, I forgot you.
Does that mean for the case of the two wires going opposite directions, does that mean that the magnetic field anywhere in space would be 0?
No.
But you can just draw a contour line that would go over any point that surrounds them both.
No. No. This will give you a magnetic field. This will give you a magnetic field, right? We know that if you have two currents, we might have attraction or repulsion, right? No, the mystery is that when I integrate over a closed contour, I will always get the current inside. Yeah, doesn't mean that it's 0. Just like Gauss, remember? No, it doesn't mean. It needs some thinking, okay? We can prove it mathematically. And that's the power of reasoning, is that we can reason it out. Can I prove it to you, give you an intuitive feeling? Maybe not. Okay, maybe not. That's why when we start leaving electrostatics and soon we're leaving magnetostatics, you will see we will depend on reasoning, i.e., mathematical manipulations a lot. We will depending to the point that when we come to Maxwell's equations and beyond, the physical intuition is gone. Okay? So it becomes a matter of faith. You either believe or not believe. All right. All right, so I have a wire, a thick wire. Now what is happening in this thick wire is that I have current that is, in this case, the current is coming out. The current is coming out, okay? So I cannot draw all of them, but imagine there's so many currents that are coming out of this, okay? So all of this is filled with current. So we know from Ampere law that B dot dl over a closed contour is always, look, now we have to be precise, is always mu naught multiplied by I. I'm going to dirty my hands here. C. So this is inside C. Okay? So this is inside of C. This is it will help me solve a problem like this. So what is the problem? The problem statement is the following. Is that I want to find the field everywhere in space. Okay? So the question is, what is B of R for R greater or equal to 0, less than infinity, everywhere in space? So I come here to the center and I say this is my R. R is the radial direction coming out of the center. Phi is this direction. Okay? Everybody understands the problem? So if I were to I'm going to use, I'll draw one more here. So if you look at it at perspective, look, I have a cylinder with a lot of current going through it, like that. Okay? So if I have I going through the entire, I'm going to differentiate between I going through the entire cylinder, going up like this, or going through it like this. Actually, in this case, it's coming out. And the I inside a specific contour. Inside a specific contour. So I that is going through the entire cylinder is the current density, which is amp per meter squared, multiplied by the area of the cylinder, right? So this is the current density, amps per meter squared. I can't push this up, so I have to, I'll use this here. Okay? So let me do this. So integrating B dot dl equals, one more time, U naught I inside C, and that equals, okay, so I'm going to take a contour. I'm going to take a contour which has a fixed radius. Let's call it R1, but it is inside the wire. It's inside the wire. Okay, so this will be mu naught inside equals mu naught J, the current density. Is the current density changing throughout this wire? No, it's constant. Multiplied by A superstar. Okay? A superstar is an A that is found on American Idol. No. A superstar, what is A superstar? Is pi R1 squared. Is pi R1 squared. Okay? So I inside equals J A, just one more step to clarify, this equals pi R1 squared I divided by A. J is I divided by A. A superstar is pi R1 squared. Okay? So finally, okay, so I'm going to follow a path, a solution path, similar to what we did when we worked with Gauss's law. What is that? I'm interested in what is the question. Let's keep track of what is the question. The question, what is B? So where does B show up? Guys, where does B show up? B shows up under the integral. So I need to extract this from here. So this is the class of problems that I cannot do unless the problem is what? Symmetric. If it's not symmetric, forget about Ampere's law, Gauss' law, all of these laws. Okay? It doesn't work. So now, is that the case? In other words, is B as I go around the contour, is B constant? Okay. Two ways to prove it. The first one is the Einsteinian way. Einsteinian? There's such word as Einsteinian way. What do I mean by Einsteinian way? Okay? I coined this for the first time today. Okay? What it means that it's a geometrical perspective. If you can get away with a geometrical perspective, that's fine, by the way. There's nothing wrong with that. Right? But there's more than one way to show it. There's more than one way. And there's the intuitive way. So the quickest way to solve this problem, you say, if I'm standing right here, will the solution be different than if I were standing here? Why? Symmetric. Do you see that? Now ask yourself, in other words, if you're here, you will see the world. Will you see the world differently if you were to stand there? That's what symmetry means, right? So if I were to stand here, I will see the world as if I were standing here. What do you mean by seeing the world? It means that I will be affected by the world in the same way. That's what seeing means, right? Okay, so I can say that the B is constant on this contour. Number two, what else can I say? What is the direction of the B? Hold on a second. What is the direction of the B? Okay, I can guess that if this is coming out, and if I will take just one wire, if I can imagine that this bundle or this chunk of copper is composed of many little wires, I can take one of them only, and grab it with my right hand and make sure that the thumb is pointing in the direction of the current. The fingers will be pointing in the direction of the B. So definitely it has to be somewhere in that direction, right? Because of symmetry, it has to be in the phi direction.
Yeah, like, is that the only way to see like symmetry?
No, I can show it in a different way. Okay? But this is an argument based on symmetry. If you want an argument based on geometry, okay, and I have shown it's here in the notes. What I do is the following, and these are not. I don't think these are in your book. What I do is that I take a line like this that goes through the center of that cylinder or the wire. This is an important argument because you will use it later on. You need to use it. So I come here and take another line which is orthogonal to this, 90 degrees. I take a one wire, one of these many infinite wires right here, and I consider the one that is mirror image of this along this line. So this one right here. Do they exist? Yes. So one more time, I take this and I take its mirror. The mirror is based on this line of symmetry. Can I do that? Yes. Okay. So this one here, then I draw a straight line between this line and my observation point, this line and my observation point. Okay? So this line, just one current line, will give me a field. We solved it, right? We solved the field due to a current line right there. Will give me a field pointing in which direction? In a direction orthogonal to the line that connects the two. So it has to be pointing in that direction where this is a 90 degree. The symmetric point will give me a field that's pointing along the line which is orthogonal to the line that intersects the two, just like the first one. Will be pointing in this direction. Add the two. One will give you components. They will give you components that are opposite in the radial direction, and they add up in the phi direction. Okay? So you can use geometry, perfect argument, or if you want to go do it quickly, you can use the symmetry argument. So clearly that these two will give you a field that is along the phi direction. Now you can add all the other currents. For each current on this side, there is a symmetric one on the other side. So the argument holds. Next, I go to any other point. Will I get the same result? Absolutely, because of symmetry. Why should they be different? Okay, so let's continue, okay? So this tells me, then once I'm done with this argument, I can come here and I say that the B has to be constant in which direction? In the phi direction. Right? It has to be constant in the phi direction. And I'm integrating over this contour. So this contour, it means that I have an arc length here, R, dr, R, d phi. There's no dr, right? Correct? Okay, so the R comes out, the phi and the phi dotted with each other, I'll get 1. The R comes out, the B is constant, so I have B, R, integrate over the entire contour. Now that I've expressed the contour in terms of d phi, I have to express the contour in the limits of d phi, which is 0 to 2 pi. So I have BR 2 pi. That equals what? That equals the I inside, what we just found out earlier. So this is pi R. R is the same as this R, so I'll drop the 1. R squared I divided by A. The pi and the pi cancel, and the R cancels with one of the R's. So I have finally B equals mu naught I divided by 2 pi, okay? This is mu naught I multiplied by R divided by the radius, okay, of the bigger circle R. So R is the radius of the wire. So this is capital R. I could have left it in terms of A, but this is more general. Okay, I R mu naught divided by 2 pi R squared. Yes.
Where does the mu naught come from?
I'm sorry?
The mu naught.
Mu naught?
Yeah.
Mu naught, unless I, here.
But it's also
Mu naught, I inside. I inside is this. I inside, I put it here. I forgot it right here. Yes? Okay, so yes.
What is that R? Is that R1?
This is R, and this is the radius of the bigger, of the big wire. I could have kept it in A because A is pi R1 squared. Okay? So let's plot this. I'm going to plot this. Well, why don't I hold on plotting it until I complete the problem? Am I done with this problem or not? Not quite, because I found B as a function of R only what? Only if I'm inside the contour. Only if I'm inside the contour. The physics is really puzzling. You will see that in a second. The physics is not straightforward. The physics is not intuitive, at least not to me. Maybe you guys will say, oh, this is intuitive. So simple. But not to me. I'll show you in a second. BR, okay, BR is mu naught I divided by 2 pi R1 squared R. So this is for R greater or equal to 0, less than R1. Okay? Now I need to find BR for R greater than capital R1. So I go back, that's much easier. I integrate b over the contour. Which contour? Right now, which contour? Right now I have to take a contour which is outside the wire. Outside the wire. Okay? So this is outside. Outside the wire, this will be mu naught I. Which I? The entire I that goes into this wire. The entire I that goes into this wire. So finally, I come up with B R for R outside greater or equal to R, of course less than infinity. This equals mu naught I divided by 2 pi R. Okay? So now if we were to plot this, I'm going to plot this as a function of the radial distance. I want to plot the field magnitude as a function of the radial distance. I only evaluated the magnitude of the field. Where is the direction of the field? The direction in the phi direction. In the phi direction. So I'm going to plot B as a function of R. The first part of it is this one. What kind of function of this? What kind of function is this? This is R1. So if R is between 0 and R1, what is the variable here? Here, R. So it's a linear function. So it's going to be growing up like this until it reaches B maximum. After that, it's going to drop as 1 over R. So there's a 1 over R dependence outside a linear growth as long as you are inside the wire. That's what I meant when I said earlier it is not intuitive at all. Right? Any questions about this? Okay? Straightforward. It's a very complex problem. The only way we managed to solve it in a simple way, because we're not done yet, because we use Ampere law. In reality, some of you might have experience in life with magnetics and electromagnetics and currents. In reality, unfortunately, the picture is not as easy as this, but this gives us an approximation. In reality, the current is not uniform. You see that? The current is not uniform. So the current depends on the frequency. And if there's no frequency, things are not exciting. But if there's a frequency, which we will learn soon, the current will be pushed to the edges. The current will be pushed to the edges, which means that there's no uniformity in the current density. Yes, and then we'll go to you.
Are we assuming that the current flowing through the wire is DC right now?
Right now, DC. Aha. We'll have to wait a week. Yes?
Can you explain that, like, the C outside part again?
Okay, so please, we finished. You understand that for the field inside the conductor, inside the current bundle, I took a contour with a variable radius. So I derived the solution. Outside, it's quite easy. Outside, guys, please, this is important. Okay, 2 minutes left. Outside, okay, if I want to find the field outside, I take a contour outside. I went over this rather quickly, but I appreciate your question. Why? Because if I want to find the field outside, I have to do the same game, meaning that I have to come here and I have to ask myself, is the B going to change as I move along? So I can use either the symmetry argument or the geometrical argument. You can do the geometry argument perfectly well here. You can do the same argument that I did to conclude that the B is pointing in that direction and it's constant as you move along the contour. And that's what allowed me to take this out, okay, and multiply by 2 pi. And that's why I ended up with this. The details are in the notes. All right? All right, guys, I'll see you. Oh, tomorrow we have a lecture, right? Tomorrow we have a makeup lecture. I'll see you tomorrow.